Hello, this is Mr. Singleton. I am one of the Associate Directors for Outward Academy, and this lesson is based around the Year 8 lesson about forces. So I want to know what you know already, see if what you've done in primary school. What are the forces that are acting on Iron Man at this point in time? So I just want you to draw a little man either on a whiteboard or on a piece of paper, depending on if you are doing this at school or at home. So draw a quick sketch of Iron Man or a stick man if you need to. Draw the arrows that represent the forces and label them. I'll give you 1 minute. That's how quick your drawing should be. Go. Okay. This is what you should have got. There is weight, and now weight is a force, and we'll come on to this a little bit more later on in the lesson. But weight is a force that pushes you down. The reaction from the ground, which is going to push him up, and then the push from his thrusters, and then opposite to that is air resistance. We are looking at forces, so we are looking at that top strand there, which also has a bit of space physics in later on, but we're going to look at forces and that section. This is the journey through the forces topic, so we're going to look at resultant forces today, then we'll look at Newton's law of motions, a bit of terminal velocity, and then how we can investigate something called terminal velocity as well, then density, and then upthrust, and so on and so forth. So we're going to start with today's lesson, which is resultant forces. If you are working at home, then on a piece of paper, write resultant forces. If you are at school, then please resultant forces underlined with today's date as well. 30 seconds, off you go. So today we are going to try and construct a free body diagram. I know you're not sure what that is at the moment, but you will do by the end of the lesson. And then the aspire is to use free body diagrams to calculate something called the resultant force. So quite a lot of new learning today. So let's make sure we get through it. So a free body diagram, because we need to know what that means before we can even make one. What we do is we put these arrows on the diagrams to show the size of the force. And it's relatively easy. The longer the arrow, the bigger the force. Now, most of the time, particularly when we get into GCSEs, there will be a scale. So let's say I want to show the force is something like 2 newtons, I would draw it 2 centimeters. And if I want to draw 8 newtons, I draw it 8 centimeters. So a free body diagram is just the diagram with some arrows on there to show which way the forces are. The bigger the arrow, the bigger the force. Nice. And so here is a free body diagram. And this is just an example of the scale here. So it's got centimeters on, so it shows that the bigger the arrow, which is lifting the plane upwards, is a bigger arrow, all right, and it's got a bigger force. The force which is bringing it down, the weight of the plane which is bringing it down, is a smaller arrow because it's a smaller force. And if I was using this scale on the side, so 1 centimeter represents 200,000 newtons, then my top arrow would be 5 centimeters and my bottom arrow would be 4 centimeters, or the arrow pointing down would be 4 centimeters. And that's what a free body diagram is, and that's how we use it. So I want you to try this one. Here is Black Widow, and there is a force of 800 newtons pushing her upwards, and a force of 800 newtons pulling her downwards. So I want you to draw a quick stick woman this time, and you have the scale there on the side, which is 1 centimeter equals 80 newtons. You might need a quite big piece of paper for this one. Okay, so I want you to try this one either on a whiteboard, if you've got your whiteboard and you're in school. If not, then on a piece of paper at home. Off you go. I'll give you 1 minute. All right. What I should have done is drawn a diagram with a 10 centimeter arrow pointing upwards and a 10 centimeter arrow pointing downwards. Okay, another one, try this one. So this is the Hulk jumping, and you've got 100,000 newtons pushing upwards and 80,000 newtons going downwards. But this time the scale's changed a little bit. So every 1 centimeter is 1,000 newtons. Off you go, 1 minute. All right, let's have a look. What you have done was drawn a line going 10 centimeters upwards and then 8 centimeters going downwards. I think if you've been able to do that, you have now been able to construct free body diagrams. And just think 10 minutes ago, you didn't even know what a free body diagram was. So you're doing an awesome job if you can draw them now. Now we're going to move on to the Aspire to try to calculate resultant forces. So what a resultant force is kind of like just the overall force. So if you look on this left-hand side with this rocket, you've got 8 newtons pushing it upwards and 2 newtons pushing it downwards. So the overall force that rocket is going to go, because they are opposite to each other, is 6 newtons upwards. Well, how do I work that out? I just use the calculation of 8 minus the 2, which equals 6 newtons. So it's just the overall force, and we call it the resultant force. So we'll have a look at this because it should be okay. So here are some more Avengers. I want you to try and work out the resultant force of each Avenger. And what you need to do is tell me the direction they are going in as well. So it's a quick maths trip through what is the overall force and which way is that force going. So either left or right, or in the case of Captain Marvel, up or down. Off you go. I'll give you 2 minutes. If you are doing this at home, you can just put 4 and then which way he's going to go and how many newtons. If you're doing this at school, you can do the same thing onto a whiteboard if you wish. You've got 1 more minute. Okay, let's go through these answers. If you haven't finished, you can just pause the video. So 4 would move to the left of the screen by 50 newtons because 100 take away the 50 is 50 and it's newtons. Black Panther would move to the right of the screen by 5 newtons. Captain Marvel is an interesting one because actually 90 take away 90 is 0 newtons, so there is no overall force. Now, if someone can tell me, or if someone can think up a way of what that means for how she moves at that point in time, then you are doing extremely well. I'll give you a couple of minutes or a couple of seconds to think about it. If there is no overall resultant force, what does that mean for how she is moving at that point in time? Right, let's see who's got it. It means that she would not move, so she would either stay still or she would stay traveling at the same speed that she was. So she'd either be stationary or traveling at a constant speed because the forces are equal. She's got no overall resultant force. It's a very hard one. It's one that comes up in GCSE. And then we've got Spider-Man. Spider-Man would move to the right of your screen and the resultant force, sorry, is 24 newtons. That is the challenge and Aspire done. So if you've been able to construct those free body diagrams, and you can also use free body diagrams to calculate resultant forces, you have done an absolutely fantastic job, and well done. So what I want you to do is wrap up this lesson by telling me what a resultant force is and how you can calculate the resultant force. If you're doing this at home, please write this on a piece of paper. It's really key. If you're doing this in school, then definitely write this into your book. So what is a resultant force and how can you calculate it? I'll give you 3 minutes. Off you go. Okay, you got 1 more minute. Okay, if you are still writing, then you can pause the video. Need to get the answers down, then this is what you should have. So the resultant force is the overall force acting on an object, and you calculate the resultant force by subtracting the two forces from each other. Now, to GCSE, well, we have to know about resultant forces that can cause objects to speed up or slow down or change the shape of an object. That's how resultant forces are used when we talk about resultant forces in GCSE. We would ask, like that Captain Marvel question I asked you, if the resultant forces were 0, then there'd be no change. But if you have a resultant force that is positive, it's going to change the shape or it's going to change the speed of the object. So this is the second lesson of the forces topic. And you should have done last lesson, you should have done about the resultant force. So I want you to tell me what the overall force of the resultant force acting on Iron Man is. So I will need a number and a direction. If you're doing this at home, then please write it on a piece of paper. If you're doing this at school, then you can write it on your whiteboard in your planners and show the teacher. I'll give you 30 seconds. Off you go. Should have is the overall force, or the resultant force is 100 newtons going upwards, because you just do that 1000 minus the 900 to give you 100 newtons, and it's going up. So we are now on to our second lesson in the forces, which is about Newton's laws of motion. If you haven't already done the resultant forces lesson, please make sure you have done that, because it will add on to this lesson. Your title, if you are at home, on a piece of paper, Newton's laws of motion. If you're in school, then in your book with the date, Newton laws of motion. I'll give you 30 seconds to get that done. Make sure it's underlined. Off you go. So what we are going to look at today, our challenge, is to describe the effects of unbalanced forces. Now we did look at this a little bit in last lesson, and then our aspire is to state and apply Newton's laws of motion. So let's have a look at Newton's laws of motion, and this is also how we can describe the effects of unbalanced forces. So objects will stay at a really steady speed, or it will stay still, and sometimes we use the word stationary, unless a resultant force acts on them. So if the resultant force is zero, so the same force is being applied to a push, and the pull force is the exact same, then that object will do one of two things. Either it will travel at its constant speed, or it will stay the same. I always think about this when you look about driving a car. I know you're a bit young for this, but if I want to stay at the same speed on the motorway, then I put the same force. I keep the force on the accelerator at the exact same. I don't push down any further and I don't lift off any further. So the resultant forces have to be equal, and if they are equal, then they will stay at the same speed or they will stay still. So my car, which is parked up at the moment, has a resultant force of 0. There is no resultant force, or the resultant force is 0 newtons. So that is the first law of. So here is a ball, and one side is being pushed 60 newtons and the other side is being pulled 60 newtons. Now that means if I was to calculate the resultant force, it would be 0. So that ball would stay the same, in the same position, if it was already not moving. If the moving, so again, this is the same situation. It's at 60 newtons one way and 60 newtons the other way. But if it was at the same, if it was already moving, then the ball would continue to move at the same speed. It would not accelerate and it would not decelerate. So if we look at this with Iron Man, okay, at this point in time, he is hovering. Now he is staying the same. He has a resultant force of 0, i.e. his thrusters are giving out the same force as weight at this point in time. So therefore his overall resultant force is 0. So he hovers in midair. However, at this point in time, Captain Marvel's resultant force are not balanced. They are unbalanced. Her thrusters are producing a much larger force than the force of weight on the Earth, so she would speed up. So that's the effect of unbalanced forces. If they are unbalanced, they will make you speed up or slow down. But if they are balanced, then they will make you stay at the same speed or stay stationary. So we're going to look at Newton's second law of motion here. So a resultant force can cause things to speed up, or what we call acceleration. And to work that out, then you can calculate the acceleration, or you can calculate the resultant force by doing the mass times by the acceleration. Now the mass is in kilograms and the acceleration is in meters per second squared. And your resultant force is in N, which is Newton. Let's look at a couple of examples. The equation there you might want to write down in your books, or definitely write down in your books. So resultant force equals mass times acceleration. And for these three situations, so what will be the force on a football needed to accelerate it by 5 meters per second squared if it has a mass of 1 kilogram? So that's the first question I want you to do. Then the next one, what is the force? What force will a spaceship need to accelerate it by 20 meters per second squared if it has a mass of 1,000 kilograms? And then the last one, what force will a horse need to accelerate by 3 meters per second if it has a mass of 400 kilograms? I will give you 3 minutes to do those questions. I want them done either on your piece of paper or in your book. And remember to write down that equation. 3 minutes, off you go. You have 1 more minute left. Okay, let's go through. So first one, the football. All you needed to do was put in. So here's your equation. You're looking for the force. So put down resultant force. Then put in equals, and then you are looking for the mass. Now the mass is 1 kilogram, and then you need to times that by the acceleration, which is times 5 meters per second squared. So the resultant force was 5 newtons. Now, just to help you, and this is I marked for GCSE physics, so I'm trying to get you as many marks and get you into really good practice at an early stage, just so you know exactly how to do these and get the full marks. If you are ever asked this in a test or an exam, then write out the equation. So resultant force equals mass times acceleration. Then put in your numbers that you have. So we could find what the mass was, and we can find what the acceleration was, and put those in, and then work out the answer, and then remember the units. That is a 3-mark question in an AQA exam in year 11. So that would get you 3 marks. If it asks you to recall the equation as well, which this is one that you do have to remember for your GCSEs, then that would be 4 marks. So 1 mark for writing the equation, 1 mark for putting in the numbers, 1 mark for getting the actual answer right, and then 1 mark for putting the units. So if for some instance or for some reason you don't actually get the answer right, like you do the calculation wrong, even though you've got your calculator with you, you can still get 3 marks because you get 1 mark for the equation, 1 mark for putting in the right numbers, 1 mark for the answer, right? You might get that wrong, but then 1 mark for the units. You're still going to get 3 of the 4 marks, and that's what I'm trying to help you with here, getting as many marks as possible, even if you get the number wrong. Which again is unlikely because you will have a calculator in your exam, but it does allow you to still get 3 of the 4 marks out of the 4 marks without actually getting the answer right. So try to remember all. So back to this one then. So the sport spaceship, you should have had 20,000 newtons, and then the force the horse will need is 1,200 newtons. So Newton's third law of motion is quite a famous one. It's often the one that's placed in movies and quoted in movies and things. So forces have an equal and opposite reaction force. So all this means is that if you've got something staying stationary, something will be pushing it up, some force will be pushing it up, and some force will be pushing it downwards, which is usually weight. So if they are equal and opposite, then it's going to stay stationary. So wherever you've got one force, something will act against it. And you can think about this like an aeroplane. So the aeroplane moving will have thrusters pushing it forwards, but as soon as it's got something pushing it forwards, there will be a force which also pushes it backwards. And that is the opposite reaction force, which would be air resistance at this point in time. So if you look at this pre-starter that I showed you at the beginning of one of the lessons, it was the first lesson, you see that there is the reaction force from the ground pushing Iron Man upwards, but there is also weight pulling him downwards. And so they are opposite and equal at that point. This is just another way to show you this third law of motion, equal and opposite forces. So this is an elephant on a trampoline. Now, obviously this is made up, but it helps to show you what I mean. So at this point in time, there is a lot of force bringing this elephant downwards, but as he bounces upwards, the force will push upwards. So there is a force bringing him upwards and then a force downwards and so on and so forth. So they push it up and then it pushes down. And if you look at this, the trampoline. So that is our challenge. Describe the effects of unbalanced forces, and you've done balanced forces. So if the forces are balanced, then the object will stay stationary or it will move at a constant speed. If you have unbalanced forces, then that will change the speed of the object. And we have gone through all of the laws of motion. So there were 3 laws of motion there that we've gone through. That is a lot to do in one lesson. So if you manage to do those 3 laws and understand them, they're doing a fantastic job. Okay, so this is lesson 3 of the physics topic for year 8, and this is all about terminal velocity. And what this is going to move on to is a practical investigating terminal velocity. So that will be the next lesson. So we're on terminal velocity today. So the title is Terminal Velocity. That needs to be in your books if you are in school with the date and both underlined. If you are at home, then please do the same thing. I'll give you 30 seconds. Off you go. So what we are going to look at today is talk about air resistance and how air resistance changes with the speed. And then we are also going to look at describe the effect of balanced forces. Really, terminal velocity is just bringing together everything we've done about with unbalanced forces and balanced forces and resultant forces. So this is just bringing it all together for you a little bit and applying a bit of that knowledge. So this is Felix. I'm not going to try and remember how to pronounce his last name, but he jumped basically from the very top of the earth and survived. He obviously had a parachute at that point, by the way. I'm not saying you should jump off an airplane or anything like that, but he jumped from the highest height possible and still survived. Now, he did travel at the end, during his flight, he traveled at 843 miles per hour. But obviously, before he hit the ground, he had to slow down to the average or the usual speed of 17 miles per hour. There's a YouTube clip there if you want to have a look at it to watch him. It's really incredible. Actually, he loses a bit of he loses control a little bit and starts free falling and spinning, but he manages to get himself sorted and pull his parachute, obviously. So the terminal velocity of a human is about 53 meters per second or 118 miles per hour. So if you jumped out of an airplane, let's say at 30,000 feet, your terminal velocity would be 53 meters per second. However, if you jumped out of an airplane at 50,000 feet, so even higher, actually your terminal velocity would be around about the same, 53 meters per second. Now, that's because at a certain point, your 2 forces balance out. And you know from your previous lessons that when forces are balanced, then the speed stays the same on the object. So the person won't accelerate anymore. Now, as you jump out of this airplane, so this person on the left, his weight is much, much greater than the air resistance. So at that point, weight is greater. The overall resultant force will be 800 newtons down, so he will accelerate down to the earth. But eventually the air resistance and the weight balance out, because he's increasing with speed that increases the air resistance. So his forces will balance out, and that's why he reaches this terminal velocity, this end speed. He won't go any faster. If you think about this in when you are running and when you are walking, okay, when you are walking, you won't feel much wind on your face. If it's a still day, you won't have much air resistance, because you're going quite slow. But as you are going, as you start to run, you will feel the wind on your face. You'll feel the increase of air resistance. So this is just showing you that air resistance will increase with speed. So same with a car. If you put your hand out the window on a car and it's going slow, you won't feel very much air resistance. Don't do this, but if you ever did it on a motorway and you put your hand out, then you would feel a lot more air resistance, because air resistance increases with speed. That first challenge is about. So air resistance increases with speed. So terminal velocity with a parachute open. So if this person now opens up his parachute, then what happens is his terminal velocity slows right down to 10 meters per second, which is then safe to land. Okay, his weight is always going to stay the same. It's always going to be 800 newtons. But what happens is, as he opens that parachute, his the air resistance will increase, and then again, though, he reaches terminal velocity. So the air resistance and the weight stay the same or are equal, which means that he won't slow down anymore. So if he opens up his parachute straight away compared to opening it up by falling a couple of thousand feet, he actually won't slow down when he hits the ground. It won't be any slower depending on where he opens up his parachute, because again he reaches a new terminal velocity, and that's a much slower terminal velocity of 10 meters per second instead of 53 meters per second. So then that's safe for him to land, and or her, for them to land. So terminal velocity is the speed reached by the time that drag or air resistance is equal to weight, and that is the fastest a skydiver can go, or anything else can go. We can talk about this with cars or anything like that. Okay, so that's what terminal velocity is. I'm going to let you write that down in your book. I will give you 1 minute. If you need longer, obviously pause the video. Okay, we're going to move on to the next slide. So that is the Aspire done. The effects of balanced forces is that you won't go any faster, or and in this case you're talking about a skydiver falling to the ground. So that skydiver will not fall any faster to the ground, and that's because he's reached terminal velocity. However, other balanced forces we've talked about previously, if the object is already stationary or in the same spot and not moving, then it will stay the same in the same place. It will not move. So imagine you are Iron Man or Iron Woman. This is going to summarize all the lessons. You are flying through the air. How are you going to get back to headquarters? If you are currently flying at 50 miles per hour, what are you going to do to your forces to go faster? How much force will you need to put into your thrusters if you have a mass of 90 kilograms and want to accelerate 10 meters per second squared? What is going to slow you down? So what force is going to slow you down? And what will be the maximum speed you can go, or the maximum speed you can go be called? What's that force or that speed called? I will give you 4 minutes. This sums up everything we've done in these last 3 or 4 lessons. Off you go. Okay, you got 1 more minute left. You might need to look back in your book for that equation for the force, working out the force when you've got mass and acceleration. Okay, let's see how. So how are you going to get to headquarters? Well, you are going to have to increase your thrusters. If you are currently flying at 50 miles per hour, how are you going to go faster? You need to have unbalanced forces. How much force will you need to put into your thrusters if you have a mass of 90 kilograms and want to accelerate 10 meters per second squared? Then you need to put in 900 newtons. Remember, it's force equals mass times acceleration. What is going to slow you down? Air resistance, and a bonus if you put it increases the faster you go. And what is the maximum speed you can go called? It's terminal velocity. If you have managed to answer those questions, you have done an absolutely amazing job. Well done. Remember, if you're struggling with anything, go back to the lessons that we've gone through. Well done, guys. When we are looking at GCSE and we're talking about terminal velocity, we start to graph it and we start to look at how speed changes. So you'll have a look here. Look, speed increases as you jump out of the airplane. I'm looking at this yellow line here. So speed increases, jump out of the airplane, and then the speed stays the same. So you set the same speed, and that is obviously called terminal velocity. And then it starts to decrease. So speed starts to decrease, and that is because you've opened your parachute, and it starts to decrease, but then it will not. You'll not go any slower. So this bottom of this yellow line here, that is where the speed stays the same. And then when your speed actually hits zero, that's when you have landed. And you'll also talk about the effects of that on the moon as well. So that's what you've got to look forward to at GCSE.